Franz Forger, Breaking and Fixing Unforgeability Definition of Anamorphic Signature Scheme by Joseph Jagger and Roy Strakowski, and Roy gave the talk.
Hear me? Okay, perfect. So thanks for the great introduction. And my name is Roy Strakowski. I'll be presenting the paper Dictators, Friends, Forgers, Breaking and Fixing Unforgeability Definitions for Anamorphic Signature Schemes. And this is joint work with Joseph Jaeger. I'll begin with a little bit of motivation first, as well as some background. So anamorphic encryption was this primitive introduced by Persiano, Phan, and Young at Asiacrypt 2022. And to summarize a goal in one sentence, it essentially allows users to communicate privately, even in authoritarian settings where, say, a dictator might be able to get a user's secret keys. And the way this is done is by concealing hidden messages inside of innocuous ciphertexts. How is this actually realized? Technically, we can take a deployed primitive or deployed crypto system and provide an anamorphic extension. And this uses a double key to conceal anamorphic messages. In particular, the syntax for this, we might have we might be in a system where we're using hashed El-Gamal, RSA OAEP, or some other system. And that is specifically implements key generation, encryption, and decryption. Now to hide messages, anamorphic messages inside of these ciphertexts, we're going to use an anamorphic extension that looks like hashed El-Gamal or looks like RSA OAEP or whatever system we're using. And the syntax for this, we have anamorphic key generation, which outputs not only the public and secret key, but a double key. We have anamorphic encryption, which in addition to normal inputs, takes in the double key and anamorphic message and outputs an anamorphic ciphertext. And finally, anamorphic decryption takes in addition to the secret key, the double key and anamorphic ciphertext and outputs the anamorphic message. Now, because we want this to look like an existing primitive, we're going to require essentially a stealthiness property, which asks that ciphertexts that are honest and anamorphic ciphertexts that contain hidden messages are indistinguishable, even to a dictator who knows the secret key. Anamorphic signature schemes were proposed by Kudalowski, Persiano, Phan, Young, and Zawada at Crypto 2022. I will be referring to this work as KPPYZ. And the core idea here is that not only can we hide encrypted anamorphic messages inside of ciphertexts, we can also hide them inside of signatures as well. And this effectively enlarges the bandwidth of stealthy communication that we have. So the syntax specifically here, we might be working in a system that implements a standard signature scheme like El-Gamal signatures or RSA TSS, which has key generation, signing, and verification. And our anamorphic extension here is going to look like whatever signature that's deployed in our system. And this syntax here has anamorphic key generation, which again outputs a double key in addition to the normal keys. Anamorphic signing takes in the signing key, double key, message, and anamorphic message, and outputs an anamorphic signature. And finally, anamorphic decryption takes, in addition to the verification key and message, the double key and anamorphic signature and reveals the anamorphic message hidden within. And again, we want this indistinguishability property to ensure stealthiness. And KPPYZ also introduced a new security definition specific to anamorphic signatures in their work. How do these get deployed? Well, we might have our sender and receiver who are using a signature scheme, for example, in WhatsApp. And WhatsApp uses Schnorr to sign messages, metadata, headers, and other information. And then this is represented by the signature up above. And now the sender and receiver actually live in an authoritarian setting under a dictator represented by Sarin here. So what they do is they hide, and this dictator finally can take, for example, the sender signing key. So what the sender does is instead uses an anamorphic signature that looks exactly like Schnorr, but it hides an anamorphic message within it, and the receiver is able to decrypt. So how do we actually construct anamorphic signature schemes? I'll give a short warm-up based on RSA PSS. So here we have normal key generation of RSA PSS, and the anamorphic version is simply going to select a double key that is a symmetric key. Anamorphic signing builds on regular signing, and that regular signing samples a random value and hashes it. And anamorphic signing is simply going to change that random value to the pseudo-random encryption of an anamorphic message using the double key. And finally, to anamorphically decrypt, we simply extract that random-looking string and then decrypt it to reveal the anamorphic message. It's pretty clear this generalizes to any signature scheme that has recoverable signing randomness. In particular, a lot of KPPYZ's constructions can be viewed as this randomness replacement transform, which operates on any signature scheme that is randomness recoverable in sort of this pretty clear definition. And it also takes in any pseudo-random encryption, and then we get that anamorphic signature scheme. And it really just generalizes what I showed on the previous slide. Anamorphic signatures also have some advanced security notions. So in addition to the stealthiness notion, some authors proposed a notion called robustness. And this asks that honest signatures don't anamorphically decrypt to valid anamorphic messages. And then finally, KPPYZ proposed a notion called private anamorphism. And this asks that a recipient who knows the double key and sees honest signatures can't forge new signatures. So what did we do? We revisited these two definitions, looking at robustness and private anamorphism. I'll begin with what we did with robustness. We first observed a gap between the stated goal of robustness and its formalization. So we proposed a new dictator unforgeability definition to rectify this gap. We then looked at whether these two definitions are actually different. In particular, we found a practical attack against a previously proposed scheme that's robust. And so we were able to repair it to achieve our dictator unforgeability definition, or we were able to repair some of the schemes to do so. So now we turn to private anamorphism. And again, we observe a gap between the deployment scenario and its formalization. So we propose this time an unforgeability definition from the perspective of a recipient. Again, we are able to mount a practical attack against a natural scheme that satisfies private anamorphism, and this shows the importance of our definition. And finally, we repair a previous transform in two ways to achieve recipient unforgeability. So I'll start with this first, robustness. So it was proposed by Banfi, Giger, Hurt, Maurer, and Rito at Asiacrypt 2024. And I will be calling this BGHMR. And at a high level, it asks that honest signatures don't anamorphically decrypt to valid anamorphic messages. Why do we want this? BGHMR lists two primary motivations. The first is usability. We have a network that contains a lot of honest signatures going through it. So we want to actually be able to tell when a signature is honest or when it contains an anamorphic message. The second one is for security. Roughly, we want to prevent a dictator from initiating a fresh anamorphic channel with an anamorphic user. And BGHMR present two transforms that achieve this robustness definition. The first one we call randomness identification with PRF. And what it does is it takes any signature scheme that has this randomness identification property, and it augments it with a PRF to produce an anamorphic signature scheme. At a high level, the way it operates in anamorphic signing is by replacing the randomness with the PRF of a counter and an anamorphic message. And then to decrypt, you essentially run through all possible anamorphic messages until you find the one that produces the same randomness. BGHMR also give this randomness identification with PRF and XOR scheme, which essentially, instead of taking the PRF of the anamorphic message, it only does the counter and XORs it with the anamorphic message. Okay, so let's take a look specifically at how the robustness game is formalized by BGHMR. So we generate a set of anamorphic keys, and then we give access, the dictator access to a signed then anamorphic decryption oracle, which essentially either returns bot if we have a bit b equals 0, or we sample an honest signature and then try to anamorphically decrypt it. And then finally, the dictator wins if it's able to tell which it receives. So essentially, if any of the honest signatures anamorphically decrypt to something other than bot, the dictator can trivially win. Specifically, in the threat model that we imagine, the attacks captured by this robustness definition are that the dictator samples these new signatures. However, we think that this is not maybe, or there's an artificial restriction on this definition. In particular, the dictator has the signing key, so there's no reason to limit themselves to simply generating honest signatures. They can do any function of that they want. Moreover, the sender is going to be sending anamorphic messages in these signatures to the receiver. And the dictator might take an existing anamorphic signature and then adapt it or malleate it to give a new anamorphic signature. So we propose a new dictator unforgeability game to capture these kinds of attacks. So again, we generate our anamorphic, we run anamorphic key generation, and this time we give the verification and signing keys to the dictator. And then we give the dictator access to an anamorphic signing oracle that produces anamorphic signatures, and then an anamorphic decryption oracle they can query however they want. And then finally, we want the dictator to forge a new signature. So are these previous transforms that were proposed by KPPYZ and BGHMR dictator unforgeable? In particular, we have these special robust transforms. So do they achieve our strength and definition? The answer is no. So the next natural question is to ask, can we patch any of these transforms? And for the first two, we can, but for the last one, we cannot. So I'll briefly talk about why this is difficult by presenting a practical attack. So let's say our sender is sending an anamorphic message that says, let's meet at 2 p.m. What they do, because of the way RIDPX works, is they're going to calculate this PRF XOR the anamorphic message and then sign using that. And we're going to assume the signature is randomness recoverable, so that it's Elgamal, Schnorr, or RSA PSS. And then this is sent. The dictator now blocks this, extracts from the anamorphic signature the randomness, and then XORs it with a new anamorphic message, so anamorphic message prime. And then they re-sign using this. And finally, they forward that onto the receiver. Note that when the receiver performs anamorphic decryption, this is essentially going to be the PRF of the counter, XOR an anamorphic message, XOR another anamorphic message. And you might even be able to choose an XORed value that'll get you a meaningful message, like let's meet at 4 p.m. So this is a very critical break of this previously proposed scheme. However, we are able to show that RREP and RIDP, randomness replacement and randomness identification with PRF, are dictator unforgeable if we make some changes. The first one, if we have this strong randomness recoverable property, and if we use enough AEAD scheme as the components for randomness replacement, then we achieve dictator unforgeability. For RIDP, if we add the message to the PRF and have, again, the strong randomness recoverability property, then we get dictator unforgeability. Okay, now I'm going to turn from the perspective of a dictator to the perspective of a recipient by taking another look at private anamorphism. So what is private anamorphism? It was proposed by KPPYZ and alongside the original proposal of anamorphic signatures. The high-level goal is essentially that a recipient who knows the double key and sees honest signatures can't forge new signatures. And this is a pretty important property because we want that a recipient shouldn't learn more from an anamorphic channel such that they're able to now forge signatures on behalf of the sender. KPPYZ also provide a framework to achieve private anamorphism, which is very broad, and it specifically covers randomness replacement as a special case. So how do they formalize private anamorphism? It's specifically in the following game. We, again, run anamorphic key generation, but this time, because we have a malicious recipient, we give them the verification key and the double key. And then they get access to an honest signing oracle, and they're tasked with forging a new signature that hasn't been seen. So let's take a look at the threat model that this captures. This specifically captures a sender sending honest signatures to a malicious recipient who wants to forge. However, they're using anamorphic signatures. So they will be sending anamorphic signatures as well. Moreover, our recipient might be able to influence what the sender sends. So the recipient might say, hey, can you send the result of this computation and conceal it in an anamorphic message? And this computation might be rigged in some way. So we want to address these possible attacks and things that the recipient sees with our recipient unforgeability game. Again, in this game, we generate our anamorphic keys and give the verification and double keys to the recipient. And we also give them, again, access to the signing oracle. But this time, importantly, we give them access to an anamorphic signing oracle as well. And this represents anamorphic signatures flowing through the network to the recipient. And then finally, the recipient wants to forge an e-signature. OK, so is this definition really different from any of the private anamorphism definition? We've really only added one oracle. And as we show here, the answer is yes. In particular, we present an attack against a natural instantiation of randomness replacement. And first, I'm going to start with the ingredients we need for this attack. So with randomness replacement, if you remember, we have a signature scheme that is randomness recoverable and a pseudo-random encryption scheme, which and that produces our anamorphic signatures. So what we're going to need is we're going to need a signature scheme with a backdoor. And it's going to output its secret key when the signing randomness is equal to 0. Note that this scheme is actually still strongly enforgeable under chosen message attack. Our next ingredient we're going to need is a block cipher used in counter mode. And this is essentially going to be a PRF of a counter XOR our anamorphic message. And note that this itself is also pseudo-random. It's IND $CPA secure. So these two both achieve natural versions of security properties we want. However, we're going to show that the resulting anamorphic signature scheme is recipient forgeable. In particular, our attack works as follows. We're going to assume our sender has sent L anamorphic signatures to our receiver. What our receiver is going to do is calculate the PRF of L plus 1 and ask the sender to send that as an anamorphic message to them. The sender does so, computing the encryption of this. And because they're using counter mode, this is the PRF of L plus 1 XOR this anamorphic message, which is exactly that PRF value. So this zeroes out. This is now fed into the randomness of the signature scheme, which triggers the backdoor because that value is 0. And so the anamorphic signature is now the signing key, which gets sent to the receiver. And the receiver can now use it to forge any message of their choosing. So to revisit exactly what caused this attack, we had two issues. The first one is that the attack needed to take advantage of chosen randomness in the signature scheme. And the second is that it needed to take advantage of the ability to control the output of the pseudo-random encryption ciphertext because they know the symmetric key. So because the attack needed to leverage both of these properties, then simply immunizing either scheme against any one of them is sufficient to obtain recipient unforgeability. OK, let's start with the immunizing the signature scheme. If we require a stronger property on the signature scheme, then we can get recipient unforgeability. So in particular, the property we want is unforgeability under chosen randomness attack, which is essentially very similar to chosen message attack unforgeability, except the adversary can now query for signatures on messages and randomness of its choosing. So what kinds of schemes achieve this property? We show that RSA PSS and Rabin signatures are strongly enforgeable under chosen randomness attack. So anamorphic variants of these using randomness replacement are recipient unforgeable. However, this leaves open other schemes like Bonnet-Boyan, which was considered by KPPYZ. So we aren't able to prove that these achieve the chosen randomness security. So can we still get recipient unforgeable schemes? The answer is yes, with our next result. In particular, we can immunize now our pseudo-random encryption against the attack, the method that the attack used. So the property we're going to require is this very strong simulatability with random ciphertext property. And essentially, it asks that an adversary is unable to distinguish between ciphertexts and random samples, even knowing the symmetric key. Now, how is this possible, you might ask? Because the symmetric key is given? Well, we need to leverage ideal models to make the decryption of these random samples consistent with the key that the adversary knows. We give our definition very modularly, so our constructions that people may want to analyze can build on a variety of ideal primitives. So it might be random oracles, ideal ciphers, anything like that. And our definition is also composable. And then finally, it's achieved by randomized block cipher modes. So to conclude, we first observed gaps between definitions for anamorphic signatures and how they're formalized. We proposed 2 new definitions. We showed that these definitions are actually different, meaningfully different from previous ones because we were able to attack previous schemes in a practical way. And finally, we were able to repair some of the previous schemes to achieve our new definition. So thank you so much for listening to my talk.
Any question?
Yeah, thank you very much for the wonderful talk. I have a small question about your recipient unforgeability attack.
Yes.
You chose essentially the counter mode. Had it not been the counter mode, would the attack work?
So there are other schemes that you can use that are able to give the attack. This was just an example of one way to construct it. So yeah, other types of modes. Many deterministic modes can actually achieve the attack.
Because here you are actually trying to utilize that specific counter
Yeah.
and making it L+1 and then canceling it out.
Yes.
So that is why I was asking whether it will work with anything else also.
It'll also work with other types of many types of deterministic encryption schemes.
Thank you.
Yeah,
Thank you
the precise details of the attack will look different. But
Thank you.
yeah.
Thank you.
Other question? So I have a question. So,
Yeah.
So you mainly relies on scheme with randomness recovery. So
Yeah.
do you think that you can extend the work for scheme that does not enjoy the randomness recovery?
Yes. So in terms of recipient unforgeability, I think there can be some results that rejection sampling is able to achieve that. And then, however, for dictator unforgeability, rejection sampling likely can't achieve that, in particular because all signatures will output some kind of anamorphic message. So I think some of the properties can be achieved with other types of constructions, but they have to be analyzed on this case-by-case basis.
Great. So if not, then thanks again for the great talk.
Thank you.
So the second talk in this session is about adapter signature, new security definition, and generic construction for NP relation by Duong-Hieu, Ioannis Zanetos, Vasily Vika, and Ioannis will give the talk.
Can you hear me? Can you hear me? Okay. Good morning. I'm very grateful for the opportunity to present at this great venue. My name is Ioannis Zanetos, and I'm here to present you our work named Adapter Signatures, New Security Definition, and a Generic Construction for NP Relations. This is a joint work with Duong-Hieu, affiliated with Purdue University and Georgia Tech, Vasily Zikas at Georgia Tech, and me at Purdue University and National Technical University of Athens. So first, let's start by seeing what an adapter signature scheme consists of. An adapter signature scheme is basically 7 algorithms. The first 3 of them are of a regular signature scheme. We have the key generation algorithm that takes a security parameter and outputs a public key and a secret key. We have the signing algorithm that takes the secret key and the message to be signed and outputs a signature. And the verification algorithm which takes the public key, the message, the signature, and outputs a bit. So now we have 4 new algorithms with respect to a hard relation. So a hard relation is like a graph and the corresponding Hamiltonian circle. Let's keep this in our mind. And now we have 4 algorithms. We have the pre-sign algorithm, which takes the secret key, the message, and the statement of this hard relation and outputs what is named in the bibliography pre-signature. We have the pre-sign algorithm, pre-verification algorithm, sorry, which takes the public key, the message, the statement, and the pre-signature and outputs a bit, if it's correct. Then we have the adaptation algorithm, which takes the public key, the message, the pre-signature, and the witness to this hard relation and outputs a full signature or adapted signature as it's named in the bibliography. And then we have the extraction algorithm, which basically takes the public key, the message, the statement, the pre-signature, and the signature, and outputs either the witness or halt. Okay, so what can we do with this new 4 algorithms? So imagine we have Alice, which has generated the public key and the secret key with a normal key generation procedure, and she knows the statement of a hard relation, and she wants to know the witness. On the other side, we have Bob. Bob knows both the statement and the witness, and all he wants is a signature of Alice over a message M posted in a public bulletin board. So how this is possible? First, Alice will start and call the pre-signed algorithm with the secret key, the message that Bob wants to be signed, and the statement, and will generate a pre-signature. Then she will transfer this pre-signature through a secure communication channel to Bob. Bob now has all the information he needs to pre-verify and check if this pre-signature is indeed correct. And then with the knowledge of his witness, he is able to adapt. He knows the public key of Alice, the message, the pre-signature, and the witness, so he's able to adapt and create a full signature. Then he will upload this message and the corresponding full signature on a public bulletin board. Okay, and then Alice, she also has access to this public infrastructure, so she will read the signature, and then she will call the extraction algorithm with her public key, which she knows, the message, the statement, the pre-signature, and the full signature that Bob generated on her behalf, and she will be able to extract the witness. Now let's get to a little more practical application. So let's see how we can use adapter signatures to do atomic swaps on blockchains. So now we have Alice and Bob. Both of them has generated their public keys and secret keys with a normal generation algorithm. And basically, each one of them want to send some coins to each other, which they have agreed like in some exchange rate. This is out of our scope. So Bob wants a signature over Alice's message, which transfers some coins to him, and Alice wants the signature over MB, which basically transfers some coins from Bob to Alice. So now, assuming that we have a way to sample efficiently a statement and a witness, Bob starts by doing so. So now he knows the statement and the witness, and he will be able to generate a pre-signature named SB with your secret key, the message B, and the statement. And he will transfer the statement and this pre-signature to Alice. Alice now, she will pre-verify the creation of Bob, the pre-signature B, and then she will proceed in generating her pre-signature with her secret key A, message A, and the statement. Now she will transfer through a secure communication channel the pre-signature to Bob. Bob is the only one that knows the witness, so he's able to adapt. He knows the public key of Alice, the message of Alice, and he also knows the pre-signature which Alice transferred to him. And of course, he knows the witness. So he will generate the full signature or adapted signature, and he will post the message A and the pre-signature to the blockchain. By this time, Bob has already claimed his coins. Okay, now let's see what happens on Alice's end. Alice will read from the blockchain the full signature, sigma A, and she will call the extraction algorithm. She knows her public key, the message Alice, the pre-signature, the signature, and of course the statement. And by doing so, she will extract the witness. The next step for her is to adapt Bob's signature, pre-signature. So she knows the public key of Bob, she knows the message MB, she knows the pre-signature of Bob, and now she knows the witness because she called the extraction algorithm in the previous step. So she will be able to generate adapted signature B. Subsequently, she will post MB and sigma B, full adapted signature B, to the blockchain. So by doing so, she also claims her coins. So this scenario demonstrates how we can use adapter signatures to achieve atomic swaps on blockchains under minimal assumptions like signature verification. What other applications do we have for adapter signatures? The first is what we name a witness for a coin. So in the previous scenario, what basically happened is that we use this witness as a tool to facilitate the swap. Now there is Alice and Bob, and Alice wants to learn the witness, and she's willing to pay some Bitcoin. So in that sense, the witness has some corresponding value for the people associated with it. If we consider this as a building block, this allows us to do a more powerful application, which is multi-hop payments. So assume that Alice wants to pay Samki, and to doing so, she wants to use payment channels, and especially payment channel networks. In a nutshell, a payment channel is like a jointly controlled address on the blockchain, and both of them have locked some funds. If between two parties, both of them have locked some funds, and they can just update the balance sheet between them off-chain and then post this online for the settlement. So now Alice and Bob have one payment channel, and Bob and Samki have another payment channel. So since Alice and Samki don't hold the payment channel between them, what they can do is Alice will send some funds to Bob, and Bob will send some funds to Samki. So we will use Bob as an intermediate. How can we do this? Samki will sample a statement and a witness, and she will propagate the statement to Alice and Bob. Then Samki will generate a pre-signature, send to Bob, Bob will do the same, and send to Alice. And then Samki will adapt the pre-signature. So by doing so, Bob will be able to extract and adapt Alice's signature. So in that sense, the witness now corresponds to a receipt that Alice paid Samki through Bob. So let's talk about the security of AES. I'm Ariel at Asiacrypt 2021. They formalized the security. So we have the unforgeability, of course, of the underlying signature scheme. We have the sender security, which is also named witness extractability, and receiver security, which is named pre-signature adaptability. So what is witness extractability? In principle, what we want is that a sender that knows a valid pre-signature and a valid signature will always be able to extract the corresponding witness. And what is the receiver security? What we want is one that possesses a valid pre-signature with respect to some hard relation, and the witness will always be able to adapt and create a full or adapted signature. So what has been done till now in terms of adapter signatures? We have ECDSA-based adapter signatures, Schnorr-based, LWE, code-based schemes, isogeny-based schemes, and adapter signatures generated by identification schemes. So this created one natural question. Can we have adapter signatures for all NP? And Dial answered this question to the affirmative. And their construction is relatively simple. So assume that we have a normal signature scheme, then the pre-signature is basically a tuple of S bar and the statement, where S bar is the invocation of the signing algorithm on the underlying scheme with the secret key and signing the message and the statement. So in order to adapt and generate the full signature, what one should do is simply attach to this tuple the witness. And then in order to verify the full signature, what we need to do is call the verification algorithm on the underlying signature scheme with respect to the public key, the message and the statement, and of course S bar, and also verify that the statement and the witness indeed belong to language. So while it's very simple, we can see that it satisfies all the security notion introduced by Imarial. We have unforgeability of the underlying signature scheme. We have witness extractability. In principle, we only need the full signature to do so. And one is always able to adapt with an audio witness since you simply have to attach it in the tuple. But this comes with a huge security risk. The witness is exposed in plain. Let's see why this is actually a problem. So while in an atomic swap, which the witness might only be useful as a tool, it might be okay. In a scenario for witness for a coin, it's not. So the motivating motivating application for adapter signatures is blockchain. And blockchain is a public infrastructure. So if Alice and Bob have agreed to swap to some rate to exchange some BTC for a witness for a hard relation, this means that if we use dial construction, the witness is exposed in plain. So an eavesdropper that is watching the blockchain, then he can simply learn the witness. And since those two parties have agreed that it's associated with some monetary value, this means that these two parties come at a loss. So to fix this, we introduce a new security notion, which we name witness hiding. Basically, we require that for the witness Y to be extractable, we want that someone should use both the pre-signature and the full adapted signature, but not only one of them. And if we go a little more formally, we base it on the indistributability of the following two experiments. In experiment 0, we give access to the adversary to an oracle of pre-sign and adaptation to generate the signature, while on the other experiment 1, we give access to an oracle that simulates signatures without the knowledge of the witness. By doing so, now we take the question that I answered to modify it to the following. Can we have witness hiding adapter signatures for all MP? And the answer is yes. Let's see how. So first, we derive our inspiration by Sigma protocols. So a Sigma protocol between a prover and a verifier is a 3-round protocol. The prover knows the statement and the witness for a hard relation, while the verifier knows the statement. So first, the prover does a commitment, then the verifier gives him back a random challenge, and the prover will give back a response. So in that sense, a transcript is the commitment, the challenge, and the response. There is this property named special soundness of Sigma protocol. And this means that from two valid transcripts with the same commitment, but different challenges, one is able to extract the witness. And this shares some resemblance with the witness extractability of adapter signatures. Why? Because it means that from a valid pre-signature and an adapted signature, one is able to extract the witness. So now we take the IAL's construction and we modify as the following. So the pre-signature now is S bar, the statement, and a transcript of a Sigma protocol. And S bar is, of course, the calling to the underlying signature scheme with respect to the message, the statement, and now the commitment. And basically, the transcript just proves knowledge of Y. Okay, then one, in order to adapt, what you simply have to do is to keep the same commitment and response to a different challenge. And witness hiding is simply assumed by the zero knowledge property of the Sigma protocol. Okay, so after this, we made an observation, like the challenge in the pre-signature can be fixed. So we did that, and now we have a dummy message at the first part, which is now, as the pre-signature now is S bar, the statement, and the transcript where the challenge is M0, null message, all zeros. But look at that S bar is with respect to the message to be signed, not the dummy message. Okay, and then we can just use the witness to respond to, sorry, yes. We can generate the full signature by just modifying the challenge to be the message to be signed. So what we need to do this is we need to observe that the commitment is not related to the witness, and that given the commitment for a dummy message M0 and the witness, one can open the challenge to any other message, in the case the message to be signed for the pre-signature. Now let's see a Sigma protocol for the Hamiltonian circle introduced by Blau. So now the prover knows the graph and the Hamiltonian circle. And on the other hand, we have the verifier that knows the graph. So at the first step, the prover samples a permutation and commits to the permutation of the graph. Okay. The verifier has two choices, either to challenge with 0 or to challenge with 1. If he challenges with 0, then the prover should send the permutation and the corresponding openings of the permuted graph. If he chooses 1, then the prover will do the permutation of the Hamiltonian circle, which is also a Hamiltonian circle in the permuted graph, and the corresponding openings. So as we can see here too, the commitment is again not related to the witness. And one with the knowledge of the Hamiltonian circle and the transcript of Sigma protocol with challenge 0 should always be able to respond to challenge 1. So how do we go from the Sigma protocol to AES? It is known that the Hamiltonian circle is an NP-complete problem, and we have carp reduction. So with carp reduction, we can move any NP relation now to a Sigma protocol. and thus generate adapter signatures. So in a nutshell, our framework is the following. We start from NP relations, and with CARP reduction, we go to the Hamiltonian circle relations. Then one-way functions imply commitments, and with Hamiltonian circle relations and commitments, we get sigma protocols with a specific adaptable message, which is formalized in the paper. It basically refers to this M0 dummy message. And with the signatures, since we use a normal signature scheme, we have witness hiding adapter signatures for NP. So to sum up our contributions, we introduced a new security notion named witness hiding for adapter signatures. We showcase how to construct witness hiding adapter signatures for all NP. And we saw that in order to do so, witness hiding adapter signatures are implied by one-way functions. Thank you. Question.
Thank you. So any question?
Thank you for your talk. I might not have remembered the official, like the definition that you gave for witness distinguishability, but usually in the context of non-interactive zero-knowledge proofs, it's well, it's an indistinguishability notion, right? It's on simulation base. I was just wondering, why did you start looking at the indistinguishability notion as opposed to the simulation ones? And can Yuzuki property be strengthened? And
Sorry, can you come again because I didn't hear?
oh yeah, no worries. Let me put it simply. Can you strengthen your privacy zero-knowledge definition? Can you strengthen that to simulation paradigm that usually used by ASICs? It seems that you use Sigma protocols, so you should be able to do that. And it seems to me that your ZK property can be strengthened. So did you look into that problem?
So I'm not sure I understand the question. So can we take it offline?
Okay, no worries, no worries. Let's just chat after this. Thank you.
Thank you.
Thank you for your talk. Do you get a fair exchange basically with your protocol? Because it sounded like an exchange of coins, but
Okay, so
maybe it's just a fair exchange of anything.
we formalize the way to generate adapter signatures for all NP that also have the witness hiding property. Adapter signatures have been used in other works to achieve fair exchange. So it's not in our contributions, atomic swaps on blockchains. It's just a motivating state for adapter signatures, and we just demonstrated here for purposes of understanding how these primitives can be used.
Other question? So if not, let's thank the speaker again. So the last talk in this session is about security proof for existing equivalence class signature scheme by Balthazar Bauer, George Bauer, Fabian Regan, and Fabian will give the talk.
Thank you for this introduction. I have the pleasure to guide you through proofs of existing signature schemes. And as he said, this is joint work with Balthazar Bauer, who is in Versailles, and Georg Fuchsbauer, who's in Vienna. Okay, first and foremost, it probably makes sense to define what are equivalence class schemes even. And they are defined over a bilinear group, but to get an intuition to what they are used for, let's just consider one of the source groups that we will denote by G. We will denote it additively, and it will have size P, order P, and small g will be a generator. And then for the message space, we consider tuples of non-zero elements of G. And they will be partitioned in the following way, that two messages are in the same class whenever there exists a scalar mu, such that one is the multiple of the other. And maybe at this point, it is good to visualize stuff. So if we denote a message as alpha times G and beta times G, so in some sense, alpha and beta are the discrete logarithms of the components, and we then plot alpha and beta, then the classes are going to be all the lines that go through the origin, but it's a discrete set. So in this example, 1, 2 and 2, 4 lie on the blue line, so they will be in the same class. And one thing we then require of this message space is that we want it to be class hiding. That means that whenever we're given two messages, M and M prime, it should be hard to decide whether they are in the same class or not. This might seem a bit arbitrary now, but as it turns out, class hiding is in fact equivalent to assuming DDH in the group. So it is quite a natural thing that we achieve. Okay, now that we know what we're working with, how is it actually defined? And we kind of have the same structure here as we've had before. The key generation, signing and verification is going to be the same as you know it from any other signature scheme. But then we also have an adaptation mechanism that's, unfortunately, I named it the same as Yannis named it before because it is different from his talk. So this adaptation also takes a public key, a message, a signature, and the scaling factor, but it outputs a signature that's valid on the scaling factor times M. And maybe here it is important to stress that for this adaptation, you don't need to know the secret key. So someone else can give you a signature and you can adapt it privately. Okay, maybe it is good to visualize that also. So if I have a message, M that has the discrete logarithms 1 and 1 in each component, and someone else gives me a signature sigma on it, and I can use this adaptation mechanism to, for example, with the scale of 4 to get the signature sigma prime on 4, 4. Okay, now we want that adaptation of signatures in classes is easy, but we want it to be hard to go from one class to another. And that yields the definition of unforgeability. And it is defined quite similar to how you used to the definition of unforgeability for a signature scheme. So we first we run the key generation, give the public key to the forger. He then gets access to an oracle where he can ask for messages and gets back signatures on these messages. And then at some point, the forger returns a forgery. That is a message M star and the signature sigma star. And it is a forgery. He wins the game if sigma star is a valid message on M star under PK. And now in blue, here we see where the difference to the usual signature scheme and forgery game comes in. M star is supposed to be in a different class than all the messages asked before. And why is that? Well, because with the adaptation mechanism, you could trivially generate a signature on a message you haven't asked before. But if you recall, we want to assume class hiding. So what that means is that this unforgery notion now is non-falsifiable. What does that mean? That the challenger cannot efficiently check whether the adversary won the game or not. because the challenger gets a signature, but he cannot check has it been in the same class as the messages that has been asked before. And yeah, we then define the scheme as unforgeable if its advantage, which is the probability that F wins the game, is close to 0. Okay, now maybe to give you a quick example of what equivalence class signature schemes can be used for, I'll give you a quick toy demonstration of anonymous authentication. For that, Alice chooses her secret key alpha and has this H be her public key. And now we assume also that pseudonyms have been established, for example, with a proof of exponent, but that only has to happen when you establish a pseudonym. And then later, Alice only has to authenticate with her pseudonym, that is, it chooses a random mu j for every party j that it talks to, and says, hello, I am mj, and that's just mu j times g and mu j times h. And if that party now is an authority and gives it a credential sigma j, then Alice can use that credential with a different party I by choosing a new scalar mu I, authenticating with party I as mu I times g and mu I times h, and then using that credential it obtained from party j by adapting it with the factor mu I divided by mu j to get a signature on its credential, on its pseudonym for party I. And really what we gain here, that if we assume class hiding, then mi looks random, and we get an anonymity even against the signer. And the adaptation also guarantees that the credentials look random, which is a property of EQS schemes that isn't relevant for the rest of the talk today. Okay, since we get these property that we kind of get anonymity without trust, we can avoid costly serial knowledge proofs. And that's why EQS have been used for numerous cryptographic concepts. Just to give you a list of them, there has been attribute-based credentials, blind signatures, group signatures, and many, many more constructed from EQS. So what constructions of EQS actually exist? There has been the original constructions by Fuchsbauer, Hansa, and Slamanik, 2019. This construction is efficient, so signatures consist of 2 elements of the first source group and 1 element of the second group. But the downside of the original construction is that they prove unforgeability in the generic group model. Now, what is the generic group model? I will define that in detail later also, but for now it is an idealized model where we assume that the adversary has to work for any group. Then there has been another construction by Fuchsbauer and Gay, where they relaxed the unforgeability notion. In fact, they relaxed it in a way so that it becomes falsifiable. And therefore, they can get a proof from standard assumptions for this scheme. But as it turned out, this scheme was too weak for many applications. And another line of constructions has been based in the CRS model. That was by Khalili, Slamanik, and Dakhilalian. They have signatures with 8 group 1 elements and 9 group 2 elements. And then based on that work, a more efficient scheme has been constructed by Connolly, Lafourcade, and Perez-Kemper with 9 G1 elements and 4 group elements of the second group. And in the CRS model, we kind of get a trade-off that now the anonymity all of a sudden relies on the trusted setup of the CRS. Okay, and from this, both the CRS models and the relaxed unforgeability notion by Fuchsbauer and Gay are based on standard assumptions, so SXDH or the external kernel matrix diffie assumption. And based on that, we basically asked the question, is it possible to construct EQS schemes from standard assumptions? And that question was answered by us earlier this year at PKC, where we proved that no such scheme can exist. You can't prove an equivalence class scheme secure from standard assumptions. And there the question came up, does this impossibility result also apply to the CRS-based schemes? And the answer to that is no. The proof that we made considering standard assumptions does not consider the CRS model, so ad hoc you can say nothing about that. And so the intuition, it seemed, was that if you want to prove EQS secure from standard assumptions, you need to be in the CRS model. And based on that, we took a look at the CRS-based constructions, and as it turned out, the proof of these constructions, the proofs are in fact flawed, and I will go through that quickly. So I will just consider the proof of the Khalili et al. Construction, since the Coloni et al. Construction falls verbatim. And this is a proof by game hopping. And for all of you, what is game hopping? You just start with the unforgeability game, and we want to bound the probability of winning that game. And to that avail, we define a second game, game one, where we change a tiny bit of the game, and then we bound the difference in advantages, in that case by epsilon1, and then we change game one slightly again and bound the difference again by epsilon2, and so on, till we end up with game six, where in their case, where it is easy to actually bound the advantage of that game. And these hops are then used to bound the advantage of the unforgeability game by the sum of the epsilons plus the advantage of the last game, which in their case, they kind of bound with the advantage of their assumption and some negligible term. Okay, so what do they do exactly? As we've seen before, they start with this unforgeability game. Then in the first hop, they change the verification to now be verify prime. And they then argue that whenever one verification succeeds and the other one doesn't, they can construct an adversary for SXDH. And therefore, this adversary bounds the difference in advantages. This proof step works out. Then from game one to game two, they change the key generation algorithm, where they just introduce the randomness differently, but the keys are not distributed differently. So the view of the adversary does not change, and their advantages just are the same. Okay, then from game two to game three, their changes are twofold. They both change the signing algorithm and the verification. And they then argue, again, as they did in the first step, that for the verification, whenever one verification succeeds and the other one does not, they can bound that by some term. But what they forget to notice is that their sign prime is actually distributed differently from the original signing algorithm. And therefore, the view of the forger changes, as we try to visualize here by coloring that sigma I blue. And therefore, we really can't say anything about how the probability that two messages are in the same class change. And in fact, we construct an adversary that detects that event and then behaves arbitrarily. And therefore, the advantages of these games cannot be bound. Okay, now the question is, can this be fixed, or why does this happen? And the thing here is, if we recall from class heading, it is hard to decide whether two messages are in the same class. And therefore, we can't check it efficiently. And therefore, if we try to fix that proof, we cannot construct a reduction that conditions on that event. We cannot construct an efficient reduction because it cannot even detect that event efficiently. And therefore, this whole proof strategy does not work for EQS schemes. And to go into more detail, what kind of happened here is that these authors, they took a proof from a standard signature scheme and then adapted it to an EQS scheme. And for a normal signature scheme, the unforgeability game is falsifiable. So you can construct an efficient reduction that conditions on that event, but for EQS, you cannot. That is where their flaw came from. Okay, so does this mean that CRS schemes are insecure? And the answer to that is we don't know. We just can't tell. One could ask now that does there exist a proof in a different model, for example, in the generic group model? But then one could argue that we already have a scheme with a proof in the generic group model that has much better efficiency and also doesn't rely on a trusted CRS. And so in order to improve the state of the art, what we did is we looked at the original FHS construction and we gave a proof in the algebraic group model. And I will quickly explain what it's about with all these models now. So in the generic group model, whenever we have communication between an adversary and a challenger, given a group, we expect the communication to be just send group elements to the adversary, and then he sends back some group elements, and that's how games are defined. The generic group model kind of abstracts that away. So the adversary only gets the simulation of a group in some sense. So the challenger keeps an internal list of encodings, for example, clubs and spades for x1 to xn, and then gives those encodings to the adversary. And the adversary gets an oracle for the group operation and for equality. And he can ask, what is clubs plus spades? And then the challenger notes down, for me, clubs and spades equals to hearts, and he gives hearts as an answer. And then whenever at some point the adversary outputs some element diamonds, the challenger can go through his lists and backtrace representation as alpha I times xi, a linear representation of the elements of the group elements of that element. Okay. Now, what is the algebraic group model? That is a model that somehow lies between the generic group model and the standard model. And why is that? Because here the adversary actually gets all the group elements. So he, for example, he could actually compute the discrete logarithm of one of the elements because he has the actual elements, which is a thing he can't do in the generic group model. But then whenever the adversary gives back a group element, we require that there exists an extractor that can find the factors alpha I such that we have that y is equal to the linear combination of alpha times x. Okay, so what assumption do we base our proof on? And for that, I want to give you an intuition why the assumption is quite natural. So if we start with the discrete logarithm assumption for a group where we still write this group additively, that might be a bit confusing. We sample a y, then the adversary gets y times g, and it must be hard for the adversary to find y. We can expand the definitions for bilinear groups where we give the adversary both y times g and y times g hat, which is the generator of the second group. And we can make this assumption more general again, which is then called the Q1, Q2 power DL assumption, where the adversary gets y times g, y squared times g, up to y to the Q1 times g, and in the other group, he gets y times g hat up to y times y to the power of Q2 times g hat, and it must still be hard to find y. And that assumption might look a bit contrived, but it is in fact the standard assumption used in most AGM proofs. Okay, So what did we prove? In fact, we proved that for a natural number, Q and A, that's an algebraic adversary that makes Q sign inquiries, then we construct an adversary B such that the advantage of B playing the 3Q, Q plus 1 power DL game is bigger than the advantage in the unforgeability game minus this 4Q plus 1 over P minus 1, where P is again the group order. So that's a negligible term. And this theorem assumes that our group generation generates random generators. But we can also, if we don't want to assume that, we can prove the same thing from slightly stronger assumptions. Okay, thank you.
Any question?
Great talk. So are there any feasibilities from in the random oracle model? So you said the CRS proofs don't work, but what about the random oracle model?
You mean if there's any constructions in the random?
Yeah.
Or I'm not aware of that. I don't think so.
So we only have it from bilinear maps?
Yeah. As far as I'm aware, yeah.
Cool, thanks.
Other question?
Thank you for the talk. Do you have any intuition about why the primitive cannot be constructed without the CRS? Like, it doesn't seem too powerful to me, but maybe it is actually too powerful.
What do you mean it cannot be constructed?
Well, you said that from standard assumptions, we cannot construct the equivalence class scheme without the CRS. Was that correct?
I mean, we actually don't have a proven secure construction from CRS.
Oh, well, there's no negative result.
The negative result is from standard assumptions.
Yes, that's what I said.
And for CRS, there was a scheme, but it doesn't have a proof.
Okay, makes sense. But yeah, okay, no, that answers my questions. Thank you.
Cheers. Yeah, that might have been confusing in my talks and so going back and forth.
More question? So I have a question. So we know signature is a mini crypt, and from the previous talk, so witness hiding adapter signature is also in mini crypt, but here there is impossibility results. Does that implies that EQS is not in mini crypt?
What do you mean mini?
That can be constructed from one-way function.
I'm not sure I understand what you mean by mini crypt or.
In mini crypt, it means that the primitive can be constructed from one-way function.
Okay.
And so signature can be constructed from one-way function.
Yeah.
And from previous talk, we see witness hiding adapter signature can also be constructed from one-way function. But with impossibility result, does this mean that EQS cannot be constructed from one-way function only?
One-way functions, would that be? The impossibility result is that you can't construct EQS from a non-interactive security assumption. I'm not sure if one-way functions would fall under that.
Okay, so we can discuss offline.
So I'm not sure. You might, but it's a stronger assumption than I assume, yeah.
Okay. So if not, then time speaker and on the speaker in this session again.
Okay.